Yeah, okay. All right, everyone. Yeah, I hope you had a good arrival here to Buenos Aires. Test. Okay. Yeah, welcome to zkTLS Day. So my name is Thomas. Yeah, I've been working for the past years on TLSNotary. And yeah, today, welcome to zkTLS Day. So I will have the talk about zkTLS fundamentals. So the goal here is to bring us all on the same page so that we can enjoy the day together and have the same basic understanding about what zkTLS is. There are some interruptions, or is that, I don't, I would, okay. I see, okay. I will try my best. So so in this presentation, basically we'll have 3 chapters. So in the first one, I'll be talking about what is zkTLS. So that then basically means what is the problem statement we have. Also have a look at the underlying technology of TLS, and also what alternative solutions are there to make that work. And after that, we'll really have a look at the different types of zkTLS and also a short look at trusted execution environments and what sort of guarantees we can get from them. And after that, we'll zoom a little bit into the whole landscape of what's after the TLS connectioning happening, and how to do the proofs, which setups do you use, attestations, verifications, and what sort of proof flavors are there. Okay, so let's first start with what is zkTLS. So maybe at this point, one remark. So very often people approach me and then just ask, what sort of proving system are you using? So I think the expectation is a little bit that you can just slap a snark on some TLS connection and that's it, how it works. So this is not how it works. It's a little bit more involved, and we'll see later why. But nevertheless, in the end, you can do zero knowledge proofs about the TLS traffic. So I think, the name fits. Okay, so let's have a look at what's the problem we are trying to solve here. So currently, there's a lot of data online on the internet about you, like think about, I don't know, banking data, social profiles, or personal information about you. And all of this data is, it's in some sense behind authorization walls. So for example, when you do, let's say a bank transaction and you get a confirmation for that bank transaction, but now this information is only intended towards you. You cannot use that confirmation for the transaction and show that to someone else, because that party will not believe you that this is true. So the party always has to check with a third party if it's really true. So it will approach the bank and say, hey, is this really did this transaction went through? And this introduces some problems because, maybe the bank does not want to support your use case, and even if they want, there's not what's the technical solution here to do that? And now that you have a third party, there might be some legal issues here. And it's also, in some sense, the control or the control over the data is abused, for power games, because a lot of business models rely on that data. And we don't want that. So ideally, you should be able to use the data about you wherever and whenever you want, and without any strings attached. Especially without any third parties. So that's basically the problem. And now we have to zoom a little bit out. So it's about zkTLS. Maybe we'll make sure that we'll understand TLS first. So what's TLS? TLS is short for Transport Layer Security. It's a protocol which makes the web safe. So when you connect to some website, TLS ensures 2 things. The first thing is that you're connected to the right machine, and the other thing is that the traffic is encrypted. So roughly speaking, TLS has about like 3 phases. So first your browser checks the certificates from the server if they are correct. Then you have like a key exchange to derive some session secrets, and these secrets are then used for the encryption of traffic. And this way you get 2 things. There are terms for that. That is confidentiality and authenticity. So confidentiality is like that the traffic is encrypted, and authenticity means that the information you get is really from the right source or right server. So TLS is like a transport protocol, so you can combine it with application protocols, most famously HTTPS, right? So the S in HTTP is for secure, so that's HTTP together with TLS, and there are other protocols doing this combination, like WebSocket or file transfer protocol. So this is all nice, but there's one thing that's missing here in the picture, and that's that goes by the term non-repudiation. That's what I already explained in the slide before. You cannot like take data from a server and show that to a third party. That third party will have no reason to believe you. And the reasons for that is that TLS uses for the encryption uses symmetric keys. So Alice has the same key like the website. So what Alice can easily do is like come up with some fake traffic and then just encrypt it because she has the same key, and then present it and then say it came from the server. Another reason is that in TLS no signatures are used. So TLS only uses message authentication codes. So these are the technical reasons why TLS cannot offer this portable authenticity of the data. Okay, and then we'll have zkTLS, which now gives you this portability of the data. So you can go to the server, take the data, and present it to some verifier. So actually, there are a lot of use cases why you might want to do that. You could think about like maybe a government server having like data about you, and maybe you want to use that for some KYC provider, or let's say that you have some banking data and you want to show that to some creditor to get a loan. Maybe just proving that you are something on a social platform, or you're scraping like websites for the Internet Archive and want to like provide some proof that this was a real website at said time. Yeah, so a lot of use cases for this portable authenticity of the data. But it's not only that authenticity aspect, it's also privacy aspect. And by that, I mean like privacy, like a fine-grained control in the hands of the user or the prover about what data is shown. Because there may be a lot of use cases where the server API does not like offer exactly what you want to show or present. So maybe you only want to present a subset of that data to some entity, and zkTLS gives you that that fine-grained privacy control over your data and what you want to forward. Okay, so now that I'm speaking about this, maybe some people might wonder, why not simply sign the data at the source? Because in a way, that is exactly what we are working around here with zkTLS. So you could go to some website, the server signs just what it sends you, and then your browser checks the signature. It could be that easy. Yeah, but there are some strings attached here. So first, if you look at the design documents like the IETF, thinking about this is that they say that when you sign something, it should be a decision made at the application layer, because signing requires intent. So what does it mean? It means like if you sign something, there might be unforeseen unforeseen things happening, because that what you sign is basically valid for eternity. And if you do that, you should know what you sign, and that is why this decision they want to defer to the application layer, because there you know what the data is about. On the other hand, if you would sign the data, then still, I mean, if you would sign the data in TLS, like in the transport layer, you would have that browsers and servers decide about if they want to support this. And yeah, zkTLS effectively like moves that decision then to the user or the prover. So it's a balance here, like, do you see like more use cases emerging from like, yeah, having like portable data, or is it more like that, yeah, you see like consequences from that signing process everywhere? Yeah. So then there is like technical reasons. So there is yeah, performance overhead you're now introducing because you're using asymmetric cryptography for the signatures, and if you are like in some constrained environments, maybe this might be a problem. So nevertheless, there are some upcoming standards. So for example, SXG, that is like signing on the application layer. In fact, it's signing the HTTP traffic. And it's an upcoming standard, and browsers start to support that. So the idea here is that first, like, you introduce some sort of caching with authenticity for all these cloud platform, for these content delivery networks. And the other thing is also that you, in some sense, enable like offline propagation of data with authenticity. I think Chrome already supports and yeah, some browsers still need to catch up. Yeah, but this would only be for HTTP, and then you still have like that the server has to support that. So, okay, so how is this, what's currently done to mitigate this? And the current solution to do that is like access delegation. So there's a protocol for that, which is called OAuth. Probably most of you know that or have used it a lot of times. So it basically works like this, like you have a user and a web app, and the web app offers some service, and that service maybe requires access to some of your data. So what then happens is you go to that website, and then that website redirects you to the authentication server. And there then the user can basically say, yeah, I consent to, I want to give my data to that web app. And then you're basically redirected to that web app with a code. The web app can then use that code, and redeem it for an authorization token at the auth server. And then with that auth token, it can access like the resource. Maybe a use case for simple use case for this would be like a photo editing app. And it supports like accessing your Google Drive or something like this. There are some issues with this solution because, the first thing is privacy, because now the resource and the auth server, they know which web app is accessing your data, so they basically know what you want to do with your data. And the other thing is censorship. So maybe they don't like what you do with your data, and well, then they simply do not support this use case. So basically, you're censored. Okay, so that was that. So now let's talk about the different types of zkTLS, and also have a look at trusted execution environments, because there's also some sort of guarantees they can give us also, although a little bit weaker. Yeah, so in essence, there are three different ways to make TLS data portable. So the first is trusted execution environments. That's basically like a hardware enclave or hardware chip solution. And then there are like two different zkTLS flavors. One is proxy approach, where you cooperate with a party but rely on network assumptions. And the other one is multi-party computation, where you introduce a party into the TLS connection, you cooperate with it, but using cryptography. So let's briefly go through these three, how they work. So trusted execution environments, so I mean, probably most of you know them. There's SXG, yeah, from Intel or so, these enclaves. So how do they work? So you have like an operator who provides this hardware of these trusted execution environments, And now you have like a prover who wants like to get some sort of attestation or like or prove something about the TLS connection. So well, they will send what we call a claim to a trusted execution environment provider. And in that claim, they will tell, yeah, basically, please connect to that server and do this and that. And afterwards, yeah, construct a proof like this. And then you can like deliver it to some verifier. So the thing here is that in this claim, because the TEE has to access that server and that server will have data behind an authorization wall about you, you will need to provide your secrets in that claim. So in a way, it's some sort of delegation with some extra guarantees. So these extra guarantees are like, I think the TEE has some sort of, it can give you some confidentiality because it can run stuff in an encrypted form. And also you get certain authenticity guarantees because yeah, you can like be sure what sort of software that TEE executes. But nevertheless, in the end, you are trusting like the hardware manufacturer of that T and also the operator to not mount any side channel attacks. So yeah, such a solution, it's like easy to block for the server because like the operator of that T will probably use the same IP or some designated IP range for that. But the nice thing is that's legacy compatible. So yeah, you don't have to do any modifications to TLS in the wild. And it's also a lightweight solution, or relatively lightweight, because you don't have to run that much cryptography. Okay, and then we are in the proxy-based zkTLS approach. So here you're basically introducing a party into the TLS connection, but not like it is only forwarding traffic. It doesn't have the key. So there are two flavors. You have the verifier proxy and the prover proxy. Let's first have a look at the verifier proxy. So what you do here is you have the prover and the server having the TLS session keys, and then you have a verifier in between of that connection. And now, yeah, the verifier forwards every traffic to the server and traffic from the server to the prover. Yeah, in this case, your protocol soundness is dependent on the network topology. What does it mean? So if the prover is able to sneak in between the verifier and the server, what he can do is he can flip TLS bytes and so on, temper the traffic, and in the end do a proof, yeah, which is simply wrong or yeah, malicious. Also in this setting, you have a little bit like weaker privacy for the prover because the verifier has to forward the traffic somewhere, and it forwards it to the server, so he has to know the DNS name. Yeah, also it's easy to block at scale because that verifier usually is some sort of service and it uses the same IP. So in contrast, you have the prover proxy. Here you have like the prover in between the TLS, and now the verifier and the server have the keys. And in this case, now your prover privacy is dependent on network topology because as soon as the the verifier gets between the prover and the server, he can now easily decrypt the traffic, and there's no more privacy for the prover. But in this case, it's quite nice that the prover is in front of the server because now it's hard to block for the server. Again, both solutions are legacy compatible and relatively lightweight. Yeah, and then there is the multi-party computation solution that's like using cryptography. So in this case, you have the two parties working together using multi-party computation. So multi-party computation is like a phrase for protocols where you have several parties and they have private inputs and they want to compute like a function and then have a public output which they share with all or a subset of the parties in this multi-party setup. And that's exactly then how MPC-TLS works. So on this picture here, the prover and the verifier, they are now together the TLS client. That means the TLS client key is shared between prover and verifier. And now they have to cooperate with MPC to drive the TLS connection forward. So in this setting, you get like the strongest privacy guarantees for the prover. So as long as the protocol is correct and the prover has his key share, he's sure that he can maintain privacy for his data. And also because the verifier has a key share, he's pretty sure that the protocol is sound because of cryptography, because he withholds the key from the prover. So the prover can no longer like fake data from the server. Yeah, also legacy compatible. The prover is in front of the server, which is quite nice, so it's hard to block. The only downside here is you have like this very big computational and also bandwidth overhead, because you're running cryptography, MPC, that's quite heavy. Okay, so now we've had a look at how zkTLS can be instantiated, the different solutions. Now let's have a look at what's after, like maybe the TLS connection. How does the proving work? So there is either the decision, so when you set up TLS, you can have like attestations. That means you're introducing a trusted party into the game, creating attestations. But also you can do it without that. Then you have like interactive verifications. And proofs come relatively, more like in two flavors. One is like just simple disclosure proofs where you just like open some bytes of the traffic, but you can also do zero knowledge proofs. Okay, let's have a look at interactive verification first. So think about it as like you have an online phase and a verification phase. So in the online phase, the three parties are somehow running this TLS connection depending on what you decided for. And after that, you have like a verification phase. And in both phases, the verifier is the same party. So after the TLS connection, the prover presents a proof to the verifier. The downside of this approach is that you now have some overhead for the verifier because he has to take part in this online phase. So for example, if you decide to go with MPC here, you have a huge computational overhead for the verifier, but also in the other settings, you like have this online requirement now on the verifier. On the bright side, you have like no trust involved here. The prover really proves something to the verifier because the verifier doesn't have to trust the third party. But your proofs are designated verifier proofs only. So what does it mean? So when you want to prove something to a verifier, you prove it. And if you want to prove something like this to some other party, you have to do it again with a different verifier, going through the online phase and also the verification, presenting the proof. So it's not like SNARK. You have like these volatile designated verifier proofs. Yeah, but in this setting, you don't need like to run your attestation protocol. So it's a little bit simpler to implement. And now the exact opposite case, that is when you like have attestations and presentations. So the difference here is that in the first picture, you're replacing like the verifier with some sort of attester service. An example for that would be a TLSNotary server. And this creates like an attestation about the TLS traffic for you. And then the prover can take this attestation and create a presentation out of it and present it to some verifier to prove something. So it's not really a proof, that's why we call it a presentation, because here we have trust involved. The verifier has to trust the attester in this setting. The nice thing here is that you can have fully blind attestations. So this means that, for example, if you use an MPC setting here, then the attester doesn't even know to which server you're connecting, which has some extra privacy guarantees and is quite nice. Yeah, but again, verifier has to trust the attester. And one thing is pretty nice. Now you can basically, these attestations, they are now signed by the attester, so they have a life cycle, so you can reuse them. and you can use one attestation and create different presentations from that. These presentations can even be different in what they disclose, which is quite nice. Also, it is theoretically possible to combine attestations from different sources. Yeah, but you need to come up with your attestation protocol for that, or how to put that in a pod or whatever. Okay, let's do like a simple example. Maybe you want to prove that you're of legal age in Web3. So how would this work? Hypothetically, so you have a server that would be a government server. That server has like some data about you, ideally like your birth date. And then, yeah, you think about, how do I want to tackle this problem? So maybe there's not that much money here to lose. So let's go with a lightweight proxy solution here, introduce an attester into the game. And now you could you open this TLS connection with a proxy approach. That attester now attests to the traffic, or you directly prove to him that you are like over 18 from the TLS traffic. Then the attester signs it, you get like the attestation, and you can create your presentations for it and put it or feed it into a smart contract. That smart contract will then check, is the attester's signature on it legit, and do I have this attester on some whitelist? Yeah, and then trigger some business flow based on if this predicate check is successful. All right, and now we want to talk about the different proving flavors. So first, the simple one, that's what we call selective disclosure. That simply means like, or maybe I should move the mouse away. So the selective disclosure proves that's like just opening some parts of the traffic. I mean, it's pretty simple, and it can deal with most of the use cases, I think. So in general, there are two ways how you want to use this disclosure, this redaction and opening of the bytes. So the first one is you want to hide authentication secrets like passwords, I don't know, cookies, JSON web tokens, and that kind of stuff. And the other one is like for this fine-grained privacy control. Because you only want to open subsets of the response. Right. So maybe one word here about tooling. So because now what you have to do in order to support this selective disclosure is you have to parse the response. So for example, you have to parse JSON, or you have to parse HTML, but you have to like attach this extra information of byte offsets. So depending on what part of the JSON the prover basically selects, you have to like match that to a byte offset, because you have to know the byte offset for redaction or opening. And also, you cannot simply redact how you want. You have to like keep the format intact, right? Because let's think about like you just redact some parts in a JSON arbitrarily, then that is not valid JSON anymore. And so your verifier will run into problems when he again tries to parse the redacted file to check for the predicate you're trying to prove. Yeah, one or two words on how to do the verification in this example, because there are some things to look out for. So the first thing is, think about injection of arbitrary bytes and control characters. Let's say you want to prove some profile, and in that profile you have like a free text field, like putting information about yourself. Now what a prover could do, it could abuse that. It like redacts the real username, and then it adds like some info in that info box, which like tries to fool the verifier into thinking that he's a different identity. So just when you are the verifier, you have to like look out for this kind of things. And another thing is that you have like these, when you redact, you leak the length of what you redact. So for example, a use case where you have a profile and you have like your sex there, and you want to redact that, that might not work because like male is 4 letters and female 6. So yeah, you have to watch out for that. Yeah, and then there's also like the other flavor of proofs that is like doing zero knowledge proofs over the TLS data. So yeah, I think ZK proving most of us know, but basically you can prove any predicate and then hide the witness to that. So for example, you prove like that you're over 18, but you hide the birth date, or you prove that you always pay your rent on time based on some transaction history from a bank. That's basically ZK proving. And yeah, you can do it with different proving systems. Some use snarks, or maybe you want to like just use that you already have an interactive protocol. And in this case, you can use like volley-based proving systems, for example, Quicksilver, because they are quite efficient. If you don't want to deal a lot with all this proving, you can like offload it to other applications. In that case, you would just simply create ZK-friendly hashes over the transcript. And then some other proving system can use that as an input and work with that. Yeah, in general, just pick the proving system you think makes sense here, depending on your environment and constraints. Okay, and one word to TLSNotary. So TLSNotary is an open source zkTLS implementation. It's a PSE project since 2022. So it's written in Rust, and currently it uses multi-party computation to realize zkTLS. Maybe some words about the features. So we have a lot of examples, documentation, JavaScript bindings. We have a browser extension, a notary server. I put it into brackets here because there are some changes coming. So for example, the notary server we deprecated, but I think you can still fork it and use it. Yeah, and we are currently developing a plugin system to give like users of zkTLS or of TLSNotary like fine-grained access of how they want to do zkTLS, what they want to redact, and so on. Right, we also develop a proxy-based approach currently, and we need to support TLS 1.3. So these are like the next action items on our list. Oh yeah, and that's it. Thank you very much. So thanks to PSE and thanks to Ethereum Foundation. And yeah. So are there any questions, maybe? I don't know, what's the time? Do we have time? Oh, maybe not. Okay, we have time.
Hi, I wonder, is there any team or company is applying zkTLS in production?
Yes,
or even specifically, has any team using the TLSNotary in production?
Of TLSNotary, yes, I think there is, for example, zkP2P. We also have a lot of other companies here that use zkTLS in production. So just check like in the other room. I don't know, I think it's, what do we have? vLayer, Primus, Opacity.
So vLayer, Primus, Reclaim, TLSNotary. We have workshops next door, but we'll give a pitch soon. But like zkTLS in production, all these projects and companies have already customers. There's all kinds of topics like Thomas did in the introduction, like KYC stuff, financial identity. Yeah, good question, thank you.
Thanks for the talk. I was wondering if the verifier always has to know the response format of the server,
Sorry, the verifier has to know what
The format of the response from the server,
the what of the response?
like the JSON format. Like, does it need to be able to parse and keep up to date with how the server responds?
I mean, he has to implement a logic that basically verifies the predicate, and I think, yeah, I mean, in most cases you will have to parse then. Or do you have any specific use case in mind, or?
Is the verifier checking that this predicate is true and nothing else is correct, or like, is it verifying the entire response or only a subset of the data?
So and it depends on the setup. So if you like have attestations, then the attester takes part in the TLS protocol and then creates an attestation, and then you present that to a verifier, and then the verifier, yeah, of course, I mean, you have to like check for the certificate chain and all of that stuff.
I see. Okay.
But also the predicate, yeah.
Okay. I have another question. Can you expand more on why volley-based approaches are better for this?
I think because, I mean, you already have an interactive setup here. So, I mean, volley-based proving systems, they are interactive. And you already have like this interactivity baked into the protocol, so we can use that and basically don't get like this disadvantage because we already have it. And then we get, yeah, a huge performance boost from them because they're very efficient.
Hello, thank you for the lovely talk. I have also been following a bit on like the GitHub activities on the TLSNotary side of things. Noticed that you guys recently added different kind of interactive examples, for example, the interactive noir example. But when I tried reading into it, it was quite challenging to like wrap my head around how does those like CK text actually fit into what you presented just now. Would you be able to also like elaborate a bit on how those things actually like fit together?
I think you probably mean that like maybe it's the case where you like create a hash, a zk-friendly hash of like the data of the TLS transcript, and in this part you can just use that and feed this into other proving systems.
So the hashing happens in the CK proof, or maybe I just need to read more on the.
Yeah, you can basically do this, create this zk-friendly hash with Quicksilver. So basically, yeah, you prove that your data hashes to this hash. Yeah.
Gotcha.
And then you can use it.
Hi.
Hi.
We have a T implementation with a blind proxy. What is the best place to introduce the TLS attestation at the blind proxy inside of the enclave, or the parent instance, or outside?
I'm not sure. I think you can get some extra guarantees from having like zkTLS running inside T's. For example, like that you're running the correct code. That is like an extra guarantee. But apart from that, I'm not sure. Maybe we can discuss later. Yeah.
Okay, thank you.
Hey, has TLSNotary been audited?
Not so far, but maybe in the future.
More questions? Okay, thank you so much. Then we have an extra minute to pitch the workshops. Thanks, Thomas.